A very good afternoon to everyone. So I hope you have a good weekend. Um, we have been through the half of the course. There is a lecture 7, 2 more weeks to go. Um, yeah, so let's some admin announcement. If you haven't got your quiz yet, you can email me and I will take a photo for you and I email to you. Okay. Okay. So before Sanqing is here. So okay. So Sanqing posted the question on the forum from the textbook. Okay. So there's a textbook drawing two graph with shaded regions, and then asks whether is the shaded region a subspace of R2. So let me move this. So recall what's the definition of subspace. What condition you need to satisfy? Anyone can recall? What's condition you need to satisfy for the subspace? What? Okay, so contains 0. Let me name it first for H. So first of all, the 0 vector is in H. Okay. Okay, good. So if U V in H, U plus V is in H. Okay. So this one is called close under vector addition. How about the third one? How about the third one? If U is in H, C a scalar, then and CV is in H. And CV is in H. Okay, so geometrically using R2 is easier to describe. Okay, so let's say you have a U. Okay, you got a V. So they are drawn from origin in R2. So how do you add two vectors? How do you add two vectors? How do you add two vectors geometrically? Okay, so where is U plus V in this case? Okay, so I think if you learned before, you can translate your vectors anywhere. Okay, and then U plus V will be the sum of the vector U and V. Okay, so you start with U and then you move in the V direction. Then you will form U plus V. Okay, or you can draw this parallelogram here. So you can translate the horizontal vector as well, so that you form this parallelogram. So U plus V is the diagonal of this parallelogram. Okay, so this is U plus V. How about C times V? Okay, so what does C times V means? Okay, so let's say you got a U. Okay, this is 3. So 3, let's say you got a U. Okay, U. What is 2U? That's 2U. Okay, 2U means 2 times the vector. So the length should be 2 times the vector. So you extend forward so that you got 2 times U. Something like this. Okay, they should overlap, but they should overlap. Okay, how about minus V? Minus U. Okay, so when you have a minus U, then you will turn the vector around. Okay, so you go the other direction. Okay, so meaning if all scalar of all vectors is in the space, that means you got the whole line for the vector. Okay, you contain everything on the line of the vectors. Okay. So so if you heard that we are living in 3D, right? Okay. So when they say that time is another dimension, so whether time can go backward or not. So if time is another dimension, can the time go backward? So some of the philosophies say time is not a dimension, but if time is a dimension, can time go backward? And how you go backward, right? So you go backward like this. So if you watch the movie Tenet, okay, you will see that all the scene is like happening backward. Like if the apple is dropping forward, dropping down, and then when you go back in time, the apple will fall out. So this, yeah, this is a another perspective of this vector space. Vector space is we try to model the world where we live in as a vector space. We try to model the world. This is what the vector space we're trying to make. Okay. Okay. If there's more chance, we will talk a little bit more about this philosophy here. But okay, anyway, so we are close under vector addition, and then next we close under scalar multiplication. Right, the third one is close under scalar multiplication. Okay, sorry, I write too small, but you should know what I'm writing. Okay, so there are two cases here. Call it A and B. Okay, so in both cases here, you can see that 0 is always in the shaded region. Okay, so the first point is no issue with the first point. So how about second point? If U and V in H is U plus V in H. Okay, so if you pick any vectors here, suppose we are in the case A. So you add them up, are you still in the shaded region? Okay, you are right. Okay, you can imagine the different square happening here. Okay, you won't go outside the shaded region. Okay. How about B? How about B? Does there exist two vectors that when you add up, you go outside the region? How? Okay, so if you pick this one with this one, okay, maybe I use white. So you pick the x-axis and the y-axis, okay, in the right way. If you pick these two, then the sum will go outside. So that this is not close under vector addition because you went out of the subspace, went out of the shaded region. Okay, so this is not close under the what vector. So it is not subspace. So no subspace. So H is not subspace. Okay. How about A? If you scale any vector, will you go up of the shaded region? Yeah. How? If you pick this horizontal, maybe you pick the 1, 0 vector again. If you scale negatively, then you will go to the left hand side. Then you go out of the shaded region. Okay. Okay. Yeah. But B, okay, this one I need to write not close under scalar multiplication. Okay, not. But B is close under scalar multiplication, right? Because the whole line, every line is in there. Is it? Yeah. So every line is in there. So this one is close under scalar multiplication. If you pick any vector you pick, the whole line is in there. So this one is close under scalar multiplication. Okay. So both of them are not subspace. Any question? Any question? Okay. All right. Yeah, some tips for the quiz. So there's someone come to my office and ask me about how to find basis. Okay, so how to find basis for code A. Okay, how to find basis for now A. How to find basis for row A. Okay. So if you have tried exercise, you should know it now already. But let me summarize for you. So let's break into 3 cases. So how to find basis of code A? Okay, how to find basis of code A? So here A should refer to a matrix. Okay, where A is a matrix. So what you do is to find code A. So you row reduce your code A. Row reduce your A, your matrix. Okay, maybe call it A prime after you reduce it. And then you'll try and find out the pivot column of your A prime. And then you pick, sorry, I should use different. So let me label this and then one step, step 2, step 3. So column from A corresponding to A prime will be the basis of the matrix. Okay, so you row reduce your matrix and then find the pivot columns, and then from the position of the pivot columns, go back to your original matrix A, and then take the columns as your basis. Okay, is it clear or not? Or do you need examples? Is it clear? Clear? Okay. Because why? Add a warning here. Because in general, vectors from the reduced column, okay, doesn't span, do not span column of A. Okay, so typically the vectors from the reduced matrix don't span the original matrix. Okay. Okay. Next. So next, any question on how to find code A? Okay, how to find now A? So how to find size? So how to find now A? Similarly, you row reduce it again. Okay, row reduce. Row reduce what? So this time you need to row reduce your augmented matrix. Just that you add an extra 0 at the back. Okay, and then you want to see what solutions of it, right? Because now A is the solution to the homogeneous system. Okay, so when you row reduce it, and then you write your solution, write the solution as parametric vector form. For example, x is equal to x1 times v1 plus x2 times v2 plus plus x3 plus vn. Okay, but typically some vi may be 0. Okay, depend on how many pivot you have. So you have how many free variables. Other that, you can think of it as a variable times a 0 vector. So it's just 0. Okay. So some of them might be 0. So those are not zero. So excluding the zero vector, right? Excluding zero vectors, all the non-zero one will form the basis of now. So the example I did in class, I include the proof why they are the basis. So that's why the solution looks long, but you just need to find the vector out is enough using this step. Okay, and not sure it's today or tomorrow we will see a general idea of this again because we're studying vector space in general. Okay. Okay, so this one is a now A, co A. Next, row A. How about row A? How about row A? So row A is really similar to finding co A, and it's the simplest one among all. So first you row reduce your A again. Okay. Row reduce to A again, then you can immediately get the row vector which contain the pivot. They will automatically form a basis for row A. Okay. So this one doesn't like co A. Okay, co A you need to go back to original matrix to get the column, but row A you don't need. It is fine to pick the one that after reduce. Okay, because when you do row reduction, right, you are multiplying scalar to everything in the row, and then you add everything to the row. So the row is still inside the span of the original row vectors. So that's why you can pick from the reduced matrix. So I'll put a remark here. So y row A equals to row reduce A. Okay. Why are they the same? Because row elementary row operation doesn't change the span of row vectors. What do you do in elementary row vectors? You just exchange row, or you scale everything, or you add another row to the other. Right? So you are still living in the span of the original row A. Okay. And so this is the main difference between row A and co A. Co A you need to pick from the original matrix. Row A no need. You can pick from the reduced one. Yeah. Any question? No. Okay. And what is another thing? Maybe okay. Maybe we stop here for now first. The next one I will ask next time. Any no question? If no, then we go into today's lecture. Okay, so recall from last time, we introduced this vector space. So vector space is generally introduced to replace Rn. Okay, so we capture the abstract definition of Rn, what Rn has to satisfy, and then we call it a vector space. Okay, so for example, if you here 2D, 3D, 4D, the D is correspond to the dimension. What is the dimension? For example, we are living in a 3D world, but with movement is a 4D, okay? 4 dimension. So it's a XYZ plus time. Okay. So vector space have two operations. One is vector addition. Second is scalar multiplication. Okay, we keep mentioning this even from Rn. And then they have to satisfy some commutativity, associativity, and then exist the identity for additive, identity for inverse, additive inverse, and then so on. Okay. And then last time we showed that set of all infinite sequence is a vector space by defining how we add them, how we multiply by scalar. Also, we show that the set of all polynomials of degree n at most n is also a vector space. Okay. So there's one more example we haven't gone through. So there's one more example. Okay, so my principle is I will try to work out all the exercise that posed in the previous year lecture. Not even I don't do it in the class because this is a GE course. So make sure you have more example to see. Okay, so one more example is the set of all real value function defined set is a vector space. Okay, I hope that you have do some form of calculus before, even for your high school, right? Fx, fgx, gx, something like that. Okay. So so for the function, what did I write here? Functions. For discrete math, I think you guys should be quite familiar with function. But this one is a real value function. So how do we add two functions together? Okay, let me write. Let's call this set as f maybe. Okay, so let's take f and any f and g f. So how do we add them? Okay, so how do you add two functions together? So how do you add two functions together is by just compute what is f on x and then plus g on x. Okay, so what is function? So function is you need to tell me for anything I put in, you tell me what I get. Okay, so this is function. So we already know that f and g both define a function. So if I feed x to f, f will give me something. If I feed x to g, gx will give me something. Okay. So now the question is, if I feed to f plus g, what does it give me? So it gives me fx plus gx. Okay, so this is what it means. All right. Get it? Okay. So this is how we define the this is called the pointwise addition. Okay, so because every point I know how to add pointwise. And then how about scalar multiply on a function? So we'll just get c times gx. Okay. So what is how you multiply a number to a function? Okay. So every point you get me a real number, I multiply with c. Okay. This is what is cg means. Okay. Because this one makes sense because f and g are function from d to up because they are real value. Okay. So if I feed some x into f and g, it gives me a real number. Okay. And then cg is what? Cg is I combine two real numbers. Real numbers can multiply, right? Okay. So it's valid. Okay. Okay. So of course you need to check. So zero function is in there, right? So fx equal to 0 for all x is in f. Okay, it's a real value function. This one is just like I don't want to draw this because depend on what d you have. So if you fit anything to f, it gives you 0. So maybe we call this a 0 function. So I put 0 arrow. Okay, so 0 function. And Yeah. Okay. Do you need anything else? Maybe minus gx. Okay. So what is minus gx mean? So you just take minus times the value of gx is the um is the additive. Oh, sorry. Okay. Yeah. And then check that all the other axioms satisfy. Okay. So there are 6 more axioms, right? So there are 10 axioms in vector space. So this one is one of them. 1, 2, 3, 4. Wait, this is just 1 and 2. So you got 8 more to check. 8 more axioms to check. Okay. So the claim is the axiom will follow from the axioms will follow from the fact that R is vector space. Okay. So most of the example here boils down to the fact that R is a vector space. We define R to satisfy everything. And all these things are built up from this R is a vector space. Okay. Yeah, you can try and verify it. I think we won't see it again. Okay, any question on this example? No? Any question in the back? Okay. Yeah. So what do we have now? Okay. Do you all know differentiation? DDX? Differentiation. Differentiate a function. Let me detour a bit. Do you know what the differentiation is? Differentiate a function. Yeah. See before. Okay. So you generally you differentiate a function, you get another function, right? Okay. So this function form a class called differentiable function. Differentiable function. Set of differentiable function. So you can think of ddx as a linear transformation from a set of differentiable function to continuous function. Yeah, to set of continuous function. So ddx is like a it is a linear transformation. Okay. So linear transformation means what? It satisfies 2 conditions. It preserves the vector addition. So ddx of f plus g is equal to ddx f plus dx g. Okay, and also if you differentiate cf is equal to c times d dxf. Okay, so you can see that it's also a linear transformation. Okay. Yeah. Yeah. Okay, right. So next, I'll write it more formally in the docs, but now you get an idea first. Okay. So important in this class, when you listen to my lecture, right, it's important that you get idea first. Okay. After you get idea, then we will go in details, bit by bit, what you need to know, what you details you need to prove something. Okay. The most important is you get the idea first. Okay? If you don't get the idea, you must certainly ask now. Okay, next next thing is we have some property from this from the vector space, from the 10 axiom that we defined. Okay, we have about 5 of them we want to share today. Okay. Yeah, so my research is about this kind of area, vector space, and then a bit of related to graph theory, so diagram. Okay. So this topic is a bit abstract. Yeah. So when we sometimes talk about the theorem, right, will be a bit abstract, not just one plus one or two plus two or matrix. Okay. So it will be a bit abstract, and then we try to go from the abstract world to some concrete calculation. Okay. So just be ready. Okay. So first thing we can get from 10 axiom here is the zero vector is unique. Okay. So this one actually quite surprising, right? Because in the axiom, we didn't say that there's only one zero vector. We said that there's one zero vector. Okay. It turns out that if you have one, that's the only one you can have. Okay. One. Okay. With the help of the other 10 axioms, there's only one zero vector that you can find in this vector space. Okay. Regarding what vector space you live in. Okay. So you can only use these 10 condition here. Okay. Let me show you. So the zero vector is unique. Okay. So there's not many information here. Okay. If there is not many information here, we try to use contradiction, contrapositive or contradiction. So we suppose it is not unique. Okay. Suppose the zero vector is not unique. Okay. So it's not unique. So there's this 0, 1 and 0, 2. Okay. And 0, 1 not equal to 0, 2. Sorry. Okay, never mind. Just set it 0, 1 and 0, 2. Okay. And this two zero vectors. Two zero vectors. 0 and 0, 2. Okay, let's play around with this 0, 1 and 0, 2. So how do we play around with it? So 0, 1. Okay, we start with 0, 1. Is equal to 0, 1 plus 0, 2. Okay. Does this work? Since 0, 2 is a zero vector. It's a zero vector. It's a zero vector. Okay. Still remember the condition on 0? So it's better that you have this table with you now, and then you can check what I say. So you see, if you have a 0, that means u plus 0 is u. Okay. So you add the 0, 2 on the right hand side. Okay. So what can you do next? Okay. What I do is I swap them. Okay. Why can I swap them? Since u plus v equals to v plus u, because our addition is commutative. Then you check the table again, so you can swap it. So now I can get 0, 2, because 0, 1 again is a zero vector. Okay, so now we have proved that 0, 1 is equal to 0, 2. Any 0 you can get is the same 0. Okay. But we didn't include this line inside our axiom, right? But we can get this result. Okay, so we call it a theorem. Okay. So using the same method, okay. So let me write in blue. using the same method, you can prove that the inverse, the negative of vector is unique. Okay, you can use the same logic idea to try. Okay, to prove that the negative of a vector is unique as well. Okay. Okay. The next thing I want to show you is if you take a 0 times every vector is the 0 vector. Is this obvious or not? Okay, but this is not in the axiom. We didn't mention this line. Okay, so why is this true? So why, if you combine a 0 scalar with a vector, you get 0 vector. Okay, in Rn maybe it's true. Okay, because in Rn we say that when you multiply 0 to a vector, you just multiply on every entry, right? Okay, so in Rn maybe true, obvious. But if my vector space is polynomial set of polynomials, okay, or a set of real value functions or infinite sequence, is it still true? Is it still true? Or any other vector space, is it still true? Okay. So now this theorem is show you that this must be true. Okay. So why is it true? Let's see what trick we can play. So what trick can we play? So let's see. So since we want to compute OU, right? Let's start from OU. So OU is what? OU is equal to 0 plus 0 times U. Okay, because 0 vector and 0 vector is 0. And scalar multiplication distribute. Right, so we get 0 times U plus 0U. Okay. So what can we do next? So this one is distributivity. Okay. So what can we do next? Again, you get 1 OU equals 2 OU. What can you do next? Huh? Why? No, you cannot just move 1 to across. We don't have this operation. We don't have operation that you can just move something to the other side for now. We only have the 10 axiom. Right? Okay. So you have a vector here. You want to make one vector disappear. What do you have? Negative of a vector. Okay. So you can add both sides negative of a vector. So like this. Plus O equals to U. And then this is the additive inverse or negative of a vector. Additive inverse. Okay. So that you will get 0 on one side, and then you plus OU plus the 0 vector, which you get. Okay. So if somebody asks you what mathematician doing, this is what we are doing. Yeah, this is what we are doing. Okay. We just play with we start with limited rules and then play with the rules. Yeah, okay. So you get 0 times U equal to 0. Okay, good. And then do you guys want to see more? Or okay, let me show you 2 more results and then we will see if we want to prove it or not. So One more result is if you change your vectors to 0, okay, anything times a 0 vector is a 0. And then another one is, this one might seem trivial, but it's also not stated in the axiom. So what's the negative of a vector? It is actually -1 times the vectors. Okay. So do you guys want to try and prove these two, or you want to see the proof? Which one? Both? Maybe pick one. Okay, second one. Okay, second one. Let's try second one. Okay. So what's the second one? So this one may be left as exercise because it's quite similar to the previous one. So this one proof. Okay. So how to prove this? So how you relate these two, right? Okay. Maybe you don't know about this guy, but this guy you should know, right? This guy is the thing that add to you get 0. Okay. So let's see what happens if you add the opposite guy, add u to the right hand side guy. Okay. So what happened to this? Okay. So what can you do? What is u? Is u in the axiom? What is u? U is 1 times u. Okay. Well, this one is important. Maybe just now you ask why so trivial one. I will need to put this in here. Right. Okay. So this is how you made out numbers out of vectors. Okay. So this one is included here. So from vectors, you can create the scalar. So this is one. The one very important here. Because you can create scalar with vectors. Okay. So we create the number already, scalars already. So both of them has scalar with the same vectors. What can you do? You can distribute again. Okay, reverse distribute it. So if you distribute it, what do you get? This one I called it axiom 10. Distribute it, you get 1 plus -1 times u. Okay, so distribute again. It's 3. Okay, so what do you do next? 1 minus 1. No, cannot. We don't have subtraction here. Okay, never go into 1 minus 1. So 1 plus -1, we already know that 1 -1 is the thing that add to 1, you get 0. Okay, from here you already can get 0. Okay, don't go into 1 minus 1. There's no subtraction in this world. Okay, we only have addition and scalar multiplication. There's no subtraction here. Okay, so we get what? 0 times u. Okay, so are we happy now? 0 times u. Happy or not? 0 times u is what? 0, because we just proved, right? So we just prove is 0. Okay, this one is just proof. Just proven. Okay, so what's next? Are we close to the theorem yet? What's next? Huh? What? I cannot hear. What's next? Plus negative on both sides. Okay, so you get plus negative on both sides. You will get, okay, I'm being sloppy a bit. I add here because it's commutative, so you can move around. Associative, so you can add left or right. So I'm being sloppy a bit. So this one is add. Maybe add on the same side. You feel happier. Okay. So from here, I think should be obvious that -1u is equal to -u. Okay. Yeah. So usually, typically, right, when I study this course, this theorem will become my assignment question. Yeah. This is a typical assignment question they will give to those who first study this. Yeah. So it seems very easy, but you like don't know where to start. Okay, start from the 10 axiom to get this result. Okay. So this U, right, you have to think is a abstract vector space just with the 10 definition axiom. Okay, any question? Any question? Okay, let's introduce subspaces before we break. So introduce subspace again. Okay, I think this one is very familiar to you already. So last time we already introduced subspace of Rn. So this time we introduce subspace for any vector space V. Okay. First of all, is a subset of H. Does anyone not know what is a subset is? Subset. Subset. Everyone know what's a subset? Let me know if you don't know. Okay. Subset is like part is like part of the space. Okay. Part of the original space. Okay, so it's a subset H of V that is itself a vector space. Okay, so why we have these three conditions here? Because want to make sure that that subset is still a vector space. Okay, so inside, so the thing you should imagine is inside a vector space. Okay, you still have a vector space. Okay, not any arbitrary set. Okay, so for example, in the start of the class, we have a vector space R2. Okay, so here we got a vector space R2. Vector space R2. Okay, you pick part of the set. Okay, so there still need to be a vector space to be a subspace. Okay, so to be a vector space, it turns out that you just need to satisfy this three condition here. First of all, you need to make sure the zero vector is in there. Okay. And then it is closed under vector addition and it is closed under scalar multiplication. If you satisfy these three property here, okay, then the 10 axiom will satisfy. Will be satisfied. Okay. If you are free, you can go and prove it. Just using these three condition here and then prove the 10 axiom. Okay. So why? So this explains that why subspaces need these three conditions here. Because this three condition here is crucial to show that the subspace is actually a vector space itself. Okay. Get it? Get it? Okay. Okay. So should we? You want to continue or you want to take a break first? Huh? Break? Okay. Okay, let's come back at 4 o'clock and then we'll continue with examples.哎，这个是我帮他的稿子，我是上面，我查一下，我没有写清楚的话，可能要补一下。第三，查一下。哦，OK，所以我这个是这样子的，所以这个只是说你取了一些 elementary matrix 作用在 A 上面嘛，对不对？所以你就做那个 elementary operation 咯，对不对？为什么一定是matrix？你不能是因为我们知道我们可以 raw reduce A 去 identity matrix。
对。
然后我们用的只有3个步骤 ，interchange 或者 scale 或者那个 replace，
对
不对？那3种都可以表达成这种 elementary matrix。OK， 所以我们就有这一系列的。
所以这个代表还是所有的 matrix 前面的。
你所需要用到的拿来 raw reduce A 去
matrix 不是就是你刚
对，
这一个是代表一个 elementary matrix，还是说是 matrix 合起来成的一个 matrix？
合起来成了一个 matrix。
那就是代表所有的 matrix，因为它到最后都可以化简。
什么叫到最后都可以化简？
所有都能化成 matrix，就是所有都化成 identity
所以对
的一个。
没有那个是 A， 可以化简成 identity matrix 的那个 matrix 是 A，
对，
然后这个是它的那个 raw reduction 的步骤。
变成这个吗？
对 ，raw reduction 已经变成 matrix 了。
对呀，raw reduction 变成了 identity matrix。
不，你看你在做 raw reduction 的时候，其实你是等于在乘一个 elementary matrix， 可以理解吗？你看你在做 raw reduction 的时候啊，其实你每一步都在乘一个 elementary matrix。OK， 所以这是我写的这个的原因。
所以就像这样一步一步
对，
乘到个
identity matrix。
那你这个代表的是这个不是 identity？
这个不是，这个只是说每一步它会发生什么事情。
其中的一步变成
对，
再用这个继续再乘 elementary matrix。
就你需要到什么你就乘什么。OK，呀、然后这整个合在一起就变成这个 matrix 的 inverse， 因为它是一个 matrix 乘 A 拿到 identity 嘛，inverse 的定义就是这样。OK，
就是这个表格代表的意思不是那个cofactor 的定义，就是不同的行不同的列都那时候
算错了，
不一样吗？它这个算错了，
错了，
表格还不错吗？这不是课本？
我觉得应该
这个应该 A23 A1乘以 A32应该是负的吧？
啊，就是错了，是吗？只有这一个啊，这个对于所有是错了。
对，其他的都对。
对，
还有
这个不知道从哪里来的表格，我也没有看过。上次他们不知道从哪里找。OK， 所以是这一个是简单。
对。那个
OK
也没动，
yeah.
就到这一步之后，你就为了证明可以把它拆开，那你为啥在这儿自动拆开？就是全程不是为了证明这个。
对，OK， 这个才是它这个是它的重点，重点是如果是 elementary 的话，elementary matrix 的话我就可以拆开，我只是不能把 general 的 matrix 拆开。
这个是什么定义嘛？
这个是这一堂课的我没有证明过的啊。
那也
OK，
没有证明过的。
没有证明过，但是是在 theorem。就是每个 elementary matrix 的话，就是这个。你再放回去看，它是那一堂课最前面这一个，这个没有证明过。只要是 elementary 你就可以拆开。但是 general
你给我也整不过了，怎么已经来了？我怎么不懂了呢？
对哦，还有这个就这个 E1就是这个东西。
对。
然后那你A times 这个是什么意思？EI
对，这一个你要用这一个来理解。AIB 的意思说 A 把第 i 个整个换成 B， 所以这个是 I 把第 i 个整个换成 X。
那我就相当于这一列是第 i 个，我把它换成了 X。
OK， 我如果要写更好一点，我其实应该这边写个 EI 加1跟EI 减1跟一个 EI 加1比较好，这样就比较清楚。
然后放进去。
对，没有错。
A 乘以1还是圆 A，这个是 ax 等于 b 的定义，然后这个是 an， 到这儿是相当于 a 这 a 的A 的 di 列对，被换成了 b， 然后下面就是用到了这个定义，
刚才证明，
就是把它俩相等，然后 determinant 也相等。
matrix 一模一样嘛，当然它的 determinant 一定要对。
然后这个就是刚才的 theorem。
对，没错。
对。
我是想问，那比如说我有一个 matrix，然后我对它进行一个 transform，把 transform 把它 row 和 column 互换，然后我再对它进行 reduce。
row， 对 row 和 column transpose。OK， 然后
我再对它进行 reduce，然后我现在得到的就是 row 的 reduce，不就是我以前 column 的 reduce？那我现在是不是就可以用我 transpose 之后，然后我的 我 reduce 出来的那几个列，去表示我原来的那些？对。
想想，如果你拿你的 A， 然后 transpose 它，
对，
然后你 reduce 它，
对，
然后你是说 row A 等于你其实 OK， 你其实想说就是你其实想说
我刚刚灵光一现，我觉得好像
我知道，等一下我知道你要说什么，你是说 call A 等于 row AT？
对，
我想一下，我感觉好像是，
我感觉好像可以。
对，好像是，好像有。
那我求出来之后，我是不是又要把它再transfer回去？
不用 row 的话，你就直接取那个 pivot， 是吗？
我取那个 pivot 了，我照样是那种一行的，然后我现在想把它变成列的，我是要把它 transfer
一样的，就是一样的，我横直都一样，重点是它活在哪一个地方，我就知道了，你懂我的意思吗？Pole A 不是 Pole A 的话，我也可以横着写啊，只是不方便罢了。Row A 我也可以直着写，只是不方便罢了。你懂什么意思吗？一开始直我们就直嘛，如果你不要又横又直嘛，所以如果你说 Call A 是横的话，这样我就把全部 Call A 都横着来看，你懂我什么意思吗？但是这一个的话，好像我有看过诶，好像有看过。
还有人说我
没有，这个在书里没有证明的。包这本书，
没有书，感觉根本没看到过。
感觉我有看过，
可能因为我不是学这个专业。
对，感觉我有看过，好像有看过。OK， 如果有问题我再告诉你，应该是对的。
我也感觉应该是可以。
对啊，应该是对。Hello, testing. Okay. So tomorrow quiz 2. Hello. Tomorrow quiz 2 is on topic 2 only. Okay. Topic 2 is about what is it about? Topic 2 is like topic 2 is on what? Subspace. Okay, subspace. What do you need to know? Subspace. Find basis. Yeah, subspace, finding basis, and then linear combination, span. Okay. All still related to row reduction. So be prepared to do row reduction again. Okay, row reduction must know how to do. Okay. What's where we stop just now? Okay, we start with subspace. So since we talk about subspace, so we need to have example of subspace, right? If no example, we are like talking about talking on air. Okay, so first example is 0. The set containing 0 vectors is a subspace of any vector space. It's called a 0 subspace. Okay, so in this space here, there's only one thing, which is 0 vector. Okay, so why this satisfies definition of subspace? Because 0, first of all, 0 is in there. Second, two things in vectors when you add them together is in X. So there's only one you can pick. So 0. Another guy you can pick is still 0. So 0 plus 0 is 0. Okay. 0 times any scalar, what do you get? We already proved it. is 0. Okay, so it satisfies the subspace condition. So this one, for the discrete math student, right? You should know. You should link it back to the proposition we prove, which is the empty set is a subset of every set. Okay, so 0 subspace. This is a vector space version. A 0 subspace is a subspace for every vector space. Okay. Yeah. So this is a relation. Okay. The next one is Pm is a subspace of Pn if m less than n. So recall what's Pm mean. Pm means the set of all polynomials that have degree less than m or n. Okay. So do I want to show you? Let me show you. Okay. So example, Pm is a subspace of Pn if m is less than n. Okay. I want to take this chance to show you some set notation. I'm not sure if all of you learned it before. Okay. So when we use a bracket, right? This is the set. This is a bracket. Okay. So inside the bracket, we will put elements. So elements. So for example, elements in this case is a1x1, sorry, a1x plus, sorry. So start with a0 plus a1x plus a2x. Okay, before that, let me pass that one. And then plus a3s cubed all the way up to n x to the power n. Okay, and then we will write some condition after the bar. And this one is called the bar, maybe. Okay. The condition we'll put here is for all any scalars a0, a1 up to a. Okay. So if you learn discriminant before, this is the set builder notation, but a simplified one. Okay. Okay. So inside this set, it will tell you that what element is in here. Okay. It describes what element is in here. How is it look like? So let's prove that Pm is a subspace of Pn if m is less than n. So first condition is Pm, is it a subset of Pn? Okay. Is Pm a subset of Pn? Okay. So precisely means, okay, I'm getting more pure max now. So this is a subset. Okay. So to say that it is a subset, you will say that for all x is p in Pm, x is in Pn. Okay. So I think in one slide, I want to tell you all the notation here, so that we can use it easily. So for all x is in Pn, x is in Pn. Okay. So everything in a Pm, how do you write it down? How do you express it? So it is like a0 plus a1x plus all the way up to an x to the power of m, am. Okay. But you can rewrite it as a0 plus a1x plus dot 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 plus am x to the power m plus 0 times x m plus 1 plus all the way to 0 times x to the power n. so that it is actually an element in Pn. Right? Can get it? Anyone get it? Okay, yeah. I see someone. Okay. Anyone not getting it? Okay. So you need to write the element in Pm, write it in some form such that it is in the form of Pn. Okay. Any question? If not, I have to go forward. Okay, next. So this is about subset. Okay. After subset, this is the zero condition subset. So the first condition is zero vectors is in the subspace. So it's zero in Pm. Okay. Zero is in Pm actually for any M. Okay. Because you can put every other coefficient is zero, all coefficient is zero. Okay. So you get the zero. Okay. If I be explicit, I say by setting all scalars as zero, then you get the zero. Okay, so if you add, is it close under vector addition? Okay, we have already shown last time that if we add two vectors together, two vectors in the polynomials that have degree at most n, they are still polynomial degree at most n, right? If, for example, if you add degree 2 polynomials to a degree 1 polynomials, is it a degree 2 or degree 1 polynomial? Or can it be a degree 3 polynomial? Cannot, right? Okay. So if you add, so what do I want to say? So the degree of polynomial don't increase the addition. Okay. So you won't have like degree 2 polynomial plus degree 3 polynomial become degree 5 polynomials. So the degree of polynomial must be less than or equal to the maximum degree of the polynomial that you add. Make sense? Yeah. So you still stay in the world of degree less than m, almost m. Okay. So if you have a scalar multiplication, if you multiply with a scalar, does it increase your degree or not? No, right? Because you don't increase the power of x. Okay, you just change the scalar. So the degree of the polynomial is still the same. Okay. I will write it properly afterwards, but I will write down why is it true first. So close under scalar multiplication because scalar doesn't change the degree of polynomial. The degree of polynomial. There's no space. Okay, doesn't change the degree of polynomial. And vector addition doesn't add the degree of polynomial. Okay, so you're good. So that's why Pm is a subspace of Pn. Okay, so what happens if m greater than n? What happens if m greater than n? Huh? So if m is greater than n, then you can show that Pn is a subspace of Pn. Okay, because now Pn become larger. Pn contain Pn. Okay, so okay, let me draw this away. Let me draw the figure for this condition here. So you should imagine PM, Pn like this, and then Pm is like this. Okay, it's a subspace. And then the zero vector is containing here. Every subspace contains a zero. Okay. 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 So this is the picture you have to have in mind. Okay, next example is this. So if I give you a span of vectors, okay, this is a vector form. Let me copy it up. Let me copy this thing. So this one is quite important. Let's look at this here. So let's say I have a vector. So H is a subset of what? Any idea? What's the subset? What's the space it live in? What's the space of this element in this H live in? Where this guy live? Huh? R2? You sure? How many entry? 3. Okay. What? Huh? You do. Oh, you mean this is 0? No, because oh no, because how should I say? Yeah. How about this one? How about this guy? Where this guy live in? Huh? R3. Yeah. So this guy is in R3. Okay. So H is a subset of R3. So is 0 in there? Is 0 in H? Yes. Okay. So how do you find 0 vector in this set? How do you find 0? How do you find 0 vector in H? What do you want to say? Huh? Do you have idea? Do you have answer? Someone have answer? No, say what you want to say. No, don't want to say. Okay, never mind. Don't be shy. Okay, so why 0 is in H? Okay, yeah. So you set x and t equal to 0. Then you will find H is in the set. Okay, so how about second one? So if you pick 2 vector in the set, or for any v1, v2 in H, okay, so v1 plus v2 is in H, right? Okay, so how do you do this? How do you show this? So for v1 and v2 in H, so we can let v1 equals to x1 t1 0, and v2 equals to x2 t2 0 for some x1 t1 x2 t2 in a real number. Right. Okay, so you want to add them together. Okay, I think we're pretty familiar on how to add 2 vectors. So how to add 2 vectors? We just add it term by term. Right. Okay, so x1 plus x2, t1 plus t2, and 0. 0 plus 0. Okay, so is this in H? Is this in H or not? Why? Why? Why is it in H? So to be in H, you need to make sure that first entry is in R, second entry is also in R. Okay, yeah. So because R is a vector, vector space, so it is closed under addition. So it is in R as well. Okay, so that's why I said everything boils down to the fact that real number is a vector space. Okay. Similarly, you can show that for any v1 in H, and a scalar c CV is in H as well. Okay, so for example, that is CV1. Okay, maybe I just write everything up for this case, then we will skip it next time. So let V1 be equal to X1, T1, 0 again. Okay, for sum X1, T1. Okay, CV1 is equal to C times X1, T1, 0, which is equal to, you multiply to everything. Okay, so now we come to a question. Is CX1 in R again? Is CT1 in R again? Okay, they are in R because R is a vector space. Okay, so it's closed under scalar multiplication. So they are in. Okay. Okay, maybe one question, last question before we leave this one. So, let's see, is this a vector space? I'll let you think for a bit. Is this a vector space? Sorry, is this a subspace? Or okay, what space I should put here actually? This H is a subset of what? What's this vector have to belong to? What space? How many entries? How many entries? How many entries? How many entries? Huh? 3. Okay, so it's in R3. Okay, so is this a subspace of R3? Who said no? Why? Because what is not in R? What do you mean by 1? The vector contain all 1 or what? No, 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 no. R3 meaning the whole vector is in R3. It's meaning, for example, like this is in R3. Okay, and 1, 1, 1 is also in H. Yeah. So if you want to say that it is not a subspace, you need to violate the 3 condition. Okay. So is this a subspace? Yep. Yeah. So okay, good. So this answer from the front say that this is not a subspace. Okay. Why? Because 0 vector is not in H. It's not in H. So everything in here is something xt with 1. Okay. So that this is not a subspace. So actually how this thing looks like? Any idea on how this thing looks like? Okay, I guess if I'm not wrong. Okay, so this thing should look like this. So since this is R3, right, we can still plot the R3 out. Okay, let's plot R3 out. Okay, so let's keep this as E1, E2, and E3. Okay, so there's one person in the class asked me, is there any difference of E1 in the R2, E1 in the R3, E1 in the R4? Right? Is there any difference? Any difference? Any difference? They are different. They are different. Yeah, actually. Okay. So E here just saying that where is the position of 1? Okay, and all the other is 0. So E1 in R2 will refer to 1, 0. Okay, E1 in R3 will refer to 1, 0, 0. And then E1 in R4 will be 1, 0, 0, 0. So the 1 there just represent where the number 1 has to be, and then all the rest is 0. Okay. Why we don't change the notation? Because they're lazy. Okay. Yeah, it's a convenient way to talk about it because it's quite obvious. I think it's quite obvious, right? Isn't it? Okay. I hope it's obvious to you. Okay, anyway, okay, let's come back and see where is this ST1. Okay, so where is ST1 in this diagram here? So the 1 is on the E3. Okay, so that means all of them has at least this height. Okay, and then I think everything is something like this. Okay, so actually is a plane that is if you imagine a plane on E1, E2, you shift it up by 1. Okay, you shift it up by 1. Can you imagine? So you got a 3D, and then you move the plane out. So the plane leave the 0 vector. So you don't have 0 vector in the plane anymore. Okay. Yeah. Okay. Can see it? Can see it? Okay. 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 So this one is a translation of E1, E2 plane up by 1, by length 1, by unit 1, by unit. Okay, we mess a lot of things together. So let's move this. This. Okay, so you translate the E1, E2 plane up by unit. So there's no 0 vector inside there anymore. So this one is the geometric. Okay. Okay, next. Next is let's talk about another theorem. So another theorem is, let's say we got n vectors in our vector space. Maybe yeah, n of them in a vector space V. So maybe I put a VS here, vector space V, call it V. So the span of these vectors, okay, we call it a span of V1 up to Vn. Recall what is the span of V1 up to Vn? Is a linear combination of the n vectors. A linear combination of these vectors is a vector subspace of V. Okay, I'll let you think for a minute. Can you think why is it automatically a subspace if I take a span of V1 up to Vn? Why is it a subspace? If I take a span of it, I'll let you think about 1 minute. If I have n vectors in my vector space, okay, in my vector space, I know how to add, I know how to do scalar multiplication. If I take linear combination of these vectors, okay, span of it, why this set become a vector subspace? Okay, why this set satisfy the 3 conditions? Any idea? Any idea? Any idea? Anyone? know how to see it? Want to share? Yeah. Write it into linear combination form. Okay, wait. Let me write down what we want to need to check first. So I need to check for condition here. Okay, so multiple. So I think the easiest way is to write down the how does the element looks like. Okay, how does the elements look like? So the span of v1 up to vn, right? So how does this look like? So it's like c1 times v1 plus c2 times v2 up to cn plus vn, such that for all any scalar c1 up to cn. Okay. Okay. So the element looks like this. Are these elements in V as well? Why? V. Because V is a vector space. If you take anything from the vector space, you add them together, it's still in the vector space. If you multiply a scalar, it's still in the vector space. So you add them, still in the vector space. So whatever you do with these two operations, you are still living in the vector space. Okay. So span of these vectors here is a subset of V. Okay. How about zero vector? Can you find zero vector in this span here? Oh. Set all the scalar to be zero. Okay. So by setting, because this is what we can do, right? Set 0 equals 0. Okay. So be careful, be careful when you set scalar to be 0, because let's say in the exam I trick you, I say scalar cannot be 0. So what can you do? Okay, so just be careful. Just be careful what you can do or you cannot do. Okay. Okay, 2. Close under vector addition. Okay. So if you take two vectors, add together, is it still in the span of H? Span of the vectors? Yes, right. Because you can collect the coefficient. Okay. Scalar, you multiply on the coefficient. So you still in the span of n vectors. Okay. So this one. So try for these two, try to write out in details. Okay. Then I will pause it out and then we can check. Okay. You want me to show or you can try and do it? You want to try or you want me to show? Huh? But you can ask me to show if you want. But what do you want? What do you want? Huh? Sure? Okay, sure. Yeah, let's show one. Okay. Okay, let's show again. Okay, resize. Okay, let's show it. Okay, so let's show how is it closed under vector addition. So the typical way we will write is we just take two vector of it. So I'll write V equals to the linear combination of V1 up to Vn. Okay. And write another vector as D1 up to Vn. Okay. For some C1 up to Cn and D1 up to Dn. Okay. You can notice that sometimes I use some, sometimes I use all. Okay. If I have chance, next time I will tell you, or you can ask me. Otherwise, you can just follow us. Okay. If you're really concerned, we will deal with it next time, but let me know. Okay, so we want to find what is V plus W, right? Okay, so what's V plus W? Can we write it as a linear combination of V1 up to Vn again? What do you think? What do you think? You want to add these two together. So now you have 2n terms here. Okay, but can you write it as sum of n terms? Yes or no? Yes. Okay, so what do you do? You do. Okay, so you factorize the coefficient. Okay. So you write so that you write it as a linear combination of n elements again. Okay, but C1 and D1 is in R plus R still in R. Okay, so this is a linear combination of n elements. Okay, so it is in span of V1 up to. Okay, because the coefficients satisfy the condition. Okay. Yeah. Okay. I think you can try and do it for closed under scalar multiplication. This one you can do. Okay. So the key here, in general, you need to write down the general form for element before you add. Okay. The key here is to write down the general form of your element before you do the computation. Okay. So I want to say here is start with general V W. Okay. Here is start with general V and scalar C. Okay. Yeah. Okay. 4, 3, 5. Okay. I plan to skip this example. Do you want to do or not? Do you want to do in class? This example? No. How about the rest? No. Yes. Okay. We are democratic. Okay, class. So who want to do? If you want to do, you raise hand. Then we can do together. Only a few want to do. Most of you don't want to do. Most of you don't want to do. Anyone want to do? Please lift up high. I can see if you want to do. If you want me to show together, do. Okay, do. Okay. So maybe okay, because after this we will go to the next topic, so we can spend some time here before we go to the next topic. So I'll let you try about 5 minutes. I'll also do it, then I will explain it together. I don't want to tell you how to do first, okay? You go and figure out, crack your head first. I'll do, then we check together. Try and crack your head first. First thing you need to, for this kind of question, right? You need to know what's the word, what's the definition of the word inside here. Okay. Okay, I teach you how to read first, and then you go and figure out how to do. So for this kind of new question, right? Okay, I teach you how to read first, and then you figure out how to do it. So you see, let. So given polynomials, call it P1, P2, P3, and QT. Okay, there are 3 polynomials here, 4 polynomials here. Okay, so this one easy, no need to do anything. So just give you 4 things. For what values of A? So meaning you need to find something about A. Will Q be in the subspace of P2? Okay, remember what is P2? So everything here you should be familiar already. Subspace, do you know? Satisfy the conditions, 3 condition and subset condition. P2 is what? The set of polynomial of degree at most 2. Okay, so in your mind, right, in your mind, you should pop out the set, okay, that's written as a0 plus a1x plus a2x squared and most 2. Okay, stop here. So for any scalars, a0, a1, and a2, okay. So this is the element you have in P2, spanned by P1, P2, and P3. Okay. So spanned by P1, P2, and P3 means what? Linear combination of these three things. Okay. So for what value of A will Q be in the linear combination of these three things? Everyone got it already? Everyone got it? Okay. Any question? No? Yeah, try and do it. Okay. Try and solve this question again. So for what value of A, Q can be written as the linear combination of. So maybe I write down Q equals to C1, E1 plus C2 plus D3. So sum. When you see this, I think you should be happy, right? It's some vector equation again. Some vector equation again. Okay? So try and relate what you have learned. Maybe I the question out and then I will do it, and then you also do it. Then we will compare and then see. It's okay you start, Not that not everything you can do. So it's okay that you start, but make sure that you know after you know how to do, you know where you start, how you start. Only this can keep your life going. It's not that what you know can keep you going. It's not what you don't know. Anyway, do first. You can discuss with your friend again. It's okay, you can discuss with your friend. Okay, later I will ask for the A value first before we discuss the solution, okay? If you get A, then let me. Anyone got A yet? Huh? -1? Anyone? -3. -3. Any other answer or not? 7. A equals 7. 5. 5. Okay, 5 got 2 votes. Okay. Any others? Any other got any success finding A? Okay, I don't know why I got -13. Maybe maybe we go through and then try and check where I got problem or I correct or you wrong. Not sure. Okay. Any other vote or not? Any other vote? No vote. 34. 34. Okay, good. So 1, 2, 3, 4. We got 5 choices here. 5 candidates. Okay. 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 Since I got my answer post here, so everyone check my answer. Check my working. Compared to yours. Okay. So let's recap this question again. So given 4 polynomials, you want to decide whether Q can be written as a linear combination of the given 3. Okay. So if you set out the vector equation here, you want to find C1, C2, and C3. Okay. So if you multiply them out, right, it is like this. Not yet open. So after open, something like this. Okay. So typically what you do, okay? So you compare the degree 0 part, the constant part. You compare the t part. You compare the t square part, the coefficient of t squared, right? Is this what you want to do? Okay. So why we do like this? Later we will explain why. Actually, these are the basis. So do you get this system here? This do we all get this system? Is it the same? Can we check first? Is this system correct? Hmm? Can everyone check? For those have already done. Okay. Do we have the same system? Hmm? Do we have the same system? Just now, those who tell me the answer one, can we check we have the same system first? Same system? Okay. I see one here got the same system. Okay, same system. Okay, up to here, we are all correct. Okay, all the same, at least. Okay, so here, we already got this. Okay, this is a system of linear equation. Okay, we can solve the augmented matrix. Okay, am I? Huh? What? Which one? Which one not the same? A, because here got here is positive, right? So move to the right, become negative. Huh? Everyone got the same or not? This system here. Yes? Yes? Yeah. Why? What happened? No, A is in here, right? A on the right-hand side and then move to the left. Left-hand side, move to the right-hand side, become minus. Nothing special. Unless I'm wrong here. This A here. Right? Why? Huh? Check yourself. I think most of us agree. Huh? Oh, okay, never mind. It's okay. Okay, let us check. Yeah. Okay, so system is correct, right? At least, okay, system is correct. So we proceed. So since this system is correct, make sure I don't copy wrong. Okay, so I get out this matrix. Does everyone got this matrix here? Is this the right matrix? Matrix correct or no? What? Matrix correct? Correct, huh? Okay, so I want to solve this matrix, solve the augmented matrix. Okay, so maybe something happening here. So you want to solve the augmented matrix, you want to find the pivot column. Okay, so what I do is I make the first one as a pivot. So everyone will refer back to the first row. So R2 minus R1, you get 0, minus 4 plus 5, 1, 1 minus 3 minus 2, minus 3 minus 4 minus 7. R3 minus 2 R1, okay, I get 0. Here become 10, 10 minus 7, I get 3, right? 0 minus 6, minus 6. Minus A minus 8, so minus A minus 8, right? And then what I do next is I get this become my pivot again. So I draw my pivot and then I refer row 3 to row 2. So row 3 become minus 3 row 2. So here is 0, here is 0. So minus 21. Minus 8 plus 21 is 13. So I get minus A plus 13. Anything wrong here? Last step wrong? Why? What's wrong here? Last step here. What's wrong? Minus 8 plus 5. Minus 8 plus 5. You mean this one? Minus 3. R3 minus 3 R2, right? So minus 3 times minus 7, isn't it? 21. Huh? First step, yeah. Wait, which part? This part? Which row? Oh, okay. Here. 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 Okay. Here. Okay. Isn't it 4 minus 3a? You mean this one is positive? But here, isn't it? Then what happened here? Oh, wait. Oh, wait. Okay. I see. Okay, I see. Okay, I see. Oh, yeah. Okay. I know. Okay, I know what I'm going wrong. Okay, I know what I'm going wrong here. Okay, I think I wrong at various space. So minus 4 here. So I move this over. So this one become plus. Okay, and then minus 5. Minus 5 is correct. Plus 3 also correct. Okay. So now check this t here. So this t here is 3. And then this c1 is a plus, right? And then plus again. Okay. C3 become minus. This one is minus. Okay. So forgot to change this. And then t square a correct. And then 2ct plus, this one become plus, and then 7 also become plus. Okay, so actually we are wrong. I'm wrong at the linear system part. Okay, let's change this. So plus minus plus. So plus, and then let's keep my, if I keep my b, then I change my matrix. Okay, change my matrix. So basically, this one become plus, this one become minus. Okay. So plus, minus. Okay. So actually, this is plus, minus. Okay. And then, so this one become plus, minus. Okay. So what I do is still row 1 minus row 2. So what do I get now? I get 9. And then minus 1, minus 3, minus 4. Minus 3, minus 4, still minus 7, right? Okay. Row 3 minus 2, row 1. Okay. So 7 minus 8, you get minus 1. And then check my calculation again. So minus a plus 6. Right. Is it correct or not? Let me see. Plus minus plus. Okay, first of all, let me check if this. Can we check that this matrix is correct or not? 270. Is this the right augmented matrix everyone got? If you have a minus here, meaning if you have a plus here, meaning you have a minus here, because whole row is minus, right? Okay. So this is correct. Is this what you all get? Huh? First row is wrong. First row, what happened? Minus 4. Okay, let me say again. Say again. 1, 5, minus 4. So that means my 1 is wrong. My 1 is wrong. Ah, wait. Oh, I thought this is the C. Okay, so this is minus. This is minus. Okay, so this is minus, right? Okay, so now okay. Okay, now is the sign all correct? Okay, so let's start here. So after this, everyone is different. So let me check. So minus 1. Okay, so R1 plus R2 plus R1, so R3 plus 3R2. Okay, let's get rid of this. Okay, so we get -1, -5, 3, 4, 0, -1, 2, 1, -1. And then this one is 0, -3, 6, -8, +8. Okay, and then do the last. Okay, last step before we go to right. So what do we get? 4, 0, -1, 2, -1, 0, 0, 3, 6. Right? Oh, minus. Okay, sorry. It is minus. Okay, 6, 0. So -3 plus 3. Huh? 11. No? Did I do something wrong again? Oh, here is 1. Yep. 4 plus 1. Okay, good. So -3, 8, and 4 plus 5. So 5. So A is equal to 5. Yeah, A equals to 5. Okay, good. Okay, yeah. Okay, A is equal to 5. Yeah, okay. Yeah, it's normal to make mistake, but yeah, make sure you know how to check the mistake. Yeah, any questions? So when A equals to 5, this is a consistent system. So if it is consistent, then there's infinitely many or there's one solution. So in this case, there are infinitely many because you have a free variable. So you can, it's a linear combination. Any question for the rest? Any question? If not, let's take a break until 5:05. Then we come back.
一个 vector span 在这 n 个是要相互 linearly independent。
不是啊，不是啊，
就是他们几个不一定要 linearly。
不要。
不用。
比如说你也可以，不linear independent啊，你的 span，你也可以拿它们 span 呢，你也可以拿这个两个 span，但是就是像你讲，如果它不linear independent的话，你就可以可能写成这个 span 其实就等于这个的 span。
就是我又来了。
来啊。
那这个题，他不是说，那如果我如果是这个的话，那它就不是这两个就不是 R2 的 basis
啊，不是，
就
不是
basis 的话也就是 independent。
啊，对。
但是我想知道它这个怎么判断它是在就是这个20题。
啊，也可以。OK，然后
我 reduce 完怎么看它是不是 basis 啊？
哦，你要去
我这个能理解吗？就是这个的话，就是他给它写成那个augmented 那个 matrix， 然后它是 inconsistent 嘛，说明它有3个都是。
已经做了。做了，还是 inconsistent。
对，因为 inconsistent， 它是
它不 span。
为什么？它如果是 consistent 的话，它就是都是不是，那它就 basis， 那它就是 basis。
不，你说它不 consistent 对不对？consistent 还是不 consistent？不 consistent 意思是说有一个零嘛，有一整排零。
啊，不 consistent 是无解，
解不出来。
不是不相容啊。
inconsistent 哦。
啊，就是一排是0，然后旁边是一个。
对啊，一排是0，然后我就说一排是0。对。
还有一个，
我那样
应该是无解吧？
对。
无解的话，就是它其中它这个不可以用另外2个表示啊，那就是 linear independent。
教学生长
啊， 可以这么说，但是最直接是说它不 span 哦。你可以说它是 linearly，不一定。你看，你就算有一排零，不是？假设这边是零啊，这样它还是 linearly independent。OK，看你怎么看这个问题。哦，不可以，就这样看。OK，如果假设你解成这个不是？
不，我这边还有一个数，这个不为零。
啊，对，
这个不是零，这个是一个。
对，如果你
写个五
写个5，对，写个5。这样子的话，就是说这一个东西不能够写成前面的和，所以不 span。我们不会直接说它不 linearly independent，不 linearly，这样，你明白我说吗？我都没明白。
我懂了，就是说它还是 nearly independent，但只是它不 span 而已，是这个意思吗？
这个情况是，但
这个
是
肯定不 span 在这3个里面啊，因为它根本无
对，
关前面的表示啊我现在说它是不是 basis？
不 span 就不是 basis。它要符合2个条件呢，一个是 span，一个是 linearly，只要一个不符合，它就不是 basis。
就是如果我要它 basis，我就是它又要 span 又要
对，如果你看这边如果有数字的话，有3跟4的话，他们就 linearly independent linearly dependent。对，没有啦，我只是想说，从这里单看，你不一定能够看得出来是 linearly。
应该看得出来。
可以看出是零，然后也可以看出来它不 span。
对，但是等一下讲，但是 linearly independent 是要看这里有没有数字，
为什么？
因为如果这里是0的话，不是，意思说 solution to the homogeneous equation 是0吧，所以是说这2个是 linearly independent。OK， 对，等一下给我想一下，
我这个没有错啊，我没听懂你老师，应该没有错呀。我没听
这
懂。
2个肯定是 independent，不可以相互表示啊，那跟这个也是啊。
这个是不是零有什么关系啊？
如果它不是零，如果它是比如说如果是2的话，它们这3个就不会 independent，因为它就可以用前面2个表示。
没问题啊。
这个的话就
这
linearly
有
independent。
4个列，
这3个项
他的意思是这个列可以用这前2个列表示，所以说这3个列它就不是互相的 independent。
但是这一个的话，对，但是这个就不是嘛，对不对？
对，
这就不是，对，
这就
所以
不是什么？
不是 linearly independent。
我这一行是0，我把这一行就是变成0，这一行变成0，那这行照样是0。就是我让它有个 0，我乘一个 0，然后这一行乘一个 0，那这一行不照000不照做标识。
那可是我这个题怎么做？我要
等一下给我
它
看一下。
就是，那我找 basis 的话，我就把它们3个 reduce 之后，
对，
reduce 之后，就看
没听懂。
它 span 或者它不 linearly independent，它就解决那2个问题，就是 span 和 linearly independent。
那我这个那什么叫 R2？那为什么是 R2、R3？那这个
因为它有时候题目只有2个，有时候题目3个，对不对？
那这个是这个，那它这个肯定是 R3
对呀。
那我这个是怎么看出来的？因为我画剪刀这一步没法看出来它是不是span 或者是 span 和 linearly independent。
因为它这个有3个 pivot column。
对，我就想知道它这个跟 pivot column 有什么关系？
有啊。
pivot column 是说它是 basis of 这 span of 这4个东西哦 ，basis of column M。
就我如果
对，
我如果有 pivot column 的话，就是这3列它就是base of column。那它
然后它
又怎么判它是 basis 是在 R3？
对，它在 basis of R3，这是第几课的东西啊？这是2.8课。2.8课的话是要看它 ，OK，这一课的话应该是说它要有 every 在3×3的 matrix 里面，它是，我可不可以跟你讲？就是它是 row equivalent to identity matrix，就是它有3个 ，every row 跟 every column 都有。所以如果你把这3个取出来做3×3的 matrix，你就会找到 every row 都有 pivot column，这样它就 span 哦。记得那个4个 equivalent 的那个 definition。
定义就是 span。
就是那个 identity matrix，就是 span 在R3以上的。
对，
救救我，倪老师。
对。怎么救？
把 quiz 答案告诉我。
quiz 会考。
对。
quiz 会考 basis。
会。
那我就是要证它即使那个。
对，就这两个，就是这两个，你就是要解决这两个问题就对了。
那我这个的话，那我这个就是我算到这时候，我就可以说它是就我不是刚才就是给他找到了3个 pivot column 吗？就如果我有，这是第几？那就是我现在已经找到了3个 pivot column，然后我就可以说它是在R3以上是 span 了。
对。
然后我再解决那个
linear independent 问题，对。但是同时你也解决了，对不对？
对啊，因为为什么呢？因为它
你 every row
都有。
对，你也代表你 every column 也有在这个情况下在这情况
他说什么？
就是你把 row 的给 reduce 了，就相当于你把 column 给 reduce 了，很好理解啊。
这个意思就是，如果你是3乘3的话，它就是如果你 every row 都有的话，那肯定 every column
对啊，
因为它是偶数，
这
就是相对的。
3乘3。
那就是我
刚想问一个类似的问题。就是那个什么东西，这个东西要做吗 ？Y
？Y 不用。
那 Y 不用，那我们怎么保证它这个就是？
对，早上我刚才说，就是刚才我做，就是我一开始说，只要找到这个形式，你就可以说这3个。
那他为什么一定保证这个？就是从
这个我证明啊。为什么就是这个？
你说那我不应该算一遍吗？
做题的时候不用。
现在从这个到这个是怎么来？从这个到这个。
这个你应该会啊，
就是那个
parametric 这个方。
我应该会吗？
应该会，你应该要
会。应该会。
这个第1堂课就学了。
我不会。
你怎么不会？失忆症失忆。我们第1堂课考过了这个，你怎么会不会？真的，只是这个比较长一点罢了。
这怎么写的？
你能解决吗？
不是，这个不就是正常的化简吗？
不是，从
他说这一步到这一步。
那就是这步之后，它不是组成了一个新矩阵吗？
这个
OK， we should start. I think we should start.
解决1x 加上3x。
我知道这个，他没有这个步骤，直接到这里了。
对啊，我要给它是 linear。
这想一想。
对啊，你看图就好。
那这个矩阵，
这个，
想问的是，
就是
这个怎么变成吗？
他想说的是这个矩阵一定是
等一下
independent 这3个向量形成这个矩阵。
对，一定是。
那从这里怎么看出来这个？
我等会儿。
OK，
我是把它的那个3个系数直接抄出来了，然后我直接把这3个系数直接用那个
transpose。
对，然后它就直接可以出这个矩阵了呀。为什么还要把它归类，然后一个一个去排列啊？你直接 transpose 一下，它不就是那个矩阵了吗？你把
它的原理不是这个，它的原理是因为你这一列对应的那个那个项
这一列就是一开始我列出来是这一列，然后这一列对应的项就是它那个负4啊。
我还想问这个行相等有什么特别的那个？我们为什么用的是行化简相等？化简是说行相等，为什么不能列相等？
可以用啊，只不过这样行相等比较方便。
那我们求列的时候不就列相等好了？
你求列的时候，你把列 transpose 了之后，你再 reduce 不是也是一样的效果吗？
不，我就用列相等。不行，是不是可以？
来，喂，
所以这个行不行？能不能这样子？我直接 transpose 相等。
等一下吧，我还不懂你在讲什么，讲太快了。OK， 等一下。OK， wait， let me continue first. OK， later。
逻辑。
OK， wait. OK， hey, why suddenly when I ask no question, I suddenly got a lot of questions pop up? OK， I will deal with the question later. Let me get into the topic first, and then if we finish earlier, then we'll deal with the problem you guys have. Okay. Okay. So so the next part is still similar to Rn. So we want to look at linearly independent vectors inside the set. Okay. We already looked at the span just now. Span of the vectors automatically become a subspace. So what about if you take linearly independent vectors in the set? So what is the definition of linearly independence? So an index set of a vertex of vectors v1 out to vp in the vector space is said to be linearly independent if the equation c1 v1 equals to c2 v2 plus up to cp vp equal to 0 vector has only the trivial solution. Okay, it's the same. So you want to make sure that there's only trivial solution to the homogeneous equation. Okay, this is, I hope, is what we have. So the next part here is consider P1. Okay, you have 3 vectors, and you want to show that P1, P2, P3 is a linearly independent set in P. Okay, so now your vectors is not Rn anymore. Your vectors become polynomial, right? Okay, but vector equation is still the same. You take C1 times P1, C1 times P2, C1 times P3. Okay, so C1 times P1 plus C2 times P2 plus C3 plus P3. Okay, set it equal to 0. So does this has a trivial solution? So what's the solution to this? What's the solution to this? So how to solve this? So similarly to what we did just now, so you just multiply out your equation, right? Okay, and then you find the matrix. Okay, can you quickly see what the matrix is? Can you quickly see what the matrix is? You get 4C1. Okay, maybe we just do it. 4C1 plus 3C2T, 2C3 minus 2C3T. Right, so 0. Okay, so we want 4C1 to be 4C1 plus 2C3 equals 0. And then we want 3C2T minus 2C3T equal to 0. Okay, so we get 4C1 plus 2C3. So we get so from here we can generate the matrix. So we get 4, 0, 2, and 0, 3 minus 2. Then the augmented matrix is this. Okay. Minus 1 again. Where's the minus 1? Minus 1. Minus 2 should be minus 1. Oh, okay. Okay, yeah. Okay, correct. Good. Very good. Okay. Yeah. Can you apply your method to here? You say you want to apply transpose. What's your name again? Jiang. What's your name again? Jiang. Jiang Xingyi. You say you can use transpose here, is it? So how you use it? So what you do? Okay. Okay, never mind. Okay. Yeah. Okay, so you solve this. So if this C1, C2, C3 is 0, then it is linearly independent, but it is okay. I think this one obviously is not right. You cannot have pivot on every column here, right? Because you can only have at most 2 pivot. So the pivot cannot fill all the columns. So you must have one free variable. So since it is a 2 by 3 matrix, it must have at least one free variable. Okay, so it is not a independent set. Okay, you can have at most 2. Okay. You can have at most 2 people, right? So you must have at least one free variable. Okay. So if in the terms of rank, so the rank of this matrix is at most 2. So the null space is at most at least 1. Right? Yeah. Okay. Okay. So different language, but the most important thing is you have at least one variable because this is the 2 times 3. Okay. Okay. Yeah. So you don't need to solve it, but if you want to see what's the relation between these 3, you can solve it. But otherwise, you can just say that you must have at least one free variable. Then there's a non-trivial solution to the system, homogeneous system, so that it is a linearly dependent set. Linearly, yeah, it is not a linearly. Okay, yeah. So similarly, do it for this example here. So maybe we just keep it as a homework. Okay. Next. Okay, next thing. Okay, so we have linearly independent and then we have span. So the next thing we care about is the basis. So we want to find a set of vectors to represent everything in the vectors. Okay. So this vector space might be infinite guy, but we can use finitely many guys to represent them. Okay, this is called the basis. So what's the condition we need to have? It turns out that we need 2 conditions. One, this set of bases have to be linearly independent. 2, of course, for all the vectors in the vector space, you need to write as a linear combination of this guy. So they span. So we can write, if you can do these 2 things, that means this set of vectors, we call it a basis for H. Okay, so basis of H, 2 things, linearly independent and span. Okay, so let's say, okay, maybe we do this example because we already changed our space to vectors, to polynomial instead of Rn. So if we want to show that these 3 are bases, what 2 conditions we need to show? One is what? What's the 2 condition? Linearly independent and span the span P2. Okay, so first check first. Are these elements in P2? Are these elements in P2? Yes or no? Yes, right. Because they are all polynomial of at most degree 2. Okay, so the at most power is 2. So it's in P2. Okay. So linearly independent again and again. So look at C1 times P1 plus C2 times P2 plus C3 times P3 equal to 0. Okay. So you want to solve this vector equation again. Okay. Right. Time is it? Okay. Want to do or just continue? Just tell you what to do and then you try and do. Because I think you guys have a lot of questions. So later I will leave some time for question because tomorrow is quiz, right? So I leave some time for question. And then I still have one more theorem to go. So, okay. So I will tell you what to do and then do at home and then check. Okay. Because the technique is the same. It's the same calculation again and again. Yeah. Okay. Okay. So if you do this, check this. Okay. Solve the augmented matrix as before. As before. Okay. If C1 up to C3, okay, just 3. So C3 are all 0. If only trivial solution, solve it, then P1, P2, P3 are linearly independent by definition. Okay. If not, they are linearly dependent. Okay. Same thing as previous. So span. How about span? Okay, span. So how about span? So what equation you need to consider? So you need to write. So what does span mean? So write any let me call it Q. Any Q in Pn, P2 as a linear combination of P3. Okay. So what's the difference between linearly independent and span now? The equation become a general Q instead of 0. Okay. Say that's Q. So I have a temptation to skip this. Anyone can understand this Q or not? Yes, sir. Okay, so when you write Q as a general polynomial, right? You should write Q as A1 plus B and A. Sorry, I use A0. So A1 T plus A2 T plus. So use this one to set out your augmented matrix. Okay, so you could imagine that there's no more 0 on right hand side. You have A0, A1, A2, and A3. And then when you solve the augmented matrix, you should see that whether you have a consistent or inconsistent system. Okay, if you have an inconsistent system for sum B, then there exists some vector that you can write as a linear combination. Remember the onto question, the onto question. If the matrix is not onto, it's not it's inconsistent. Remember the onto question. Yeah. Okay. So instead of 0, you set A0, A1, A2, and A3 on the right hand side. I think a bit abstract. Yeah. Any question about this? Or you want me to try and do? I'll try and do. Let's see. 5:20. Okay. I think we can do this. Okay. I want you to see that actually you are doing the same row reduction as linearly independent, just replacing the 0 vector as arbitrary vector on the right. Okay. Okay. Maybe let's try and do this. So let's try and solve part 2. Does everyone got this question? So that I can skip this, or maybe I copy to the. Okay, let's try and solve the span together and see what's the difference between checking span and checking linearly independent. Actually, they are the same, but the right-hand side get changed. Okay, let's try this. Okay. Okay, let's try 5 minutes compute this, okay? Let's do it together. I would appreciate if someone can check my step. Let's check we have the same matrix on. Okay. Everyone got the same matrix? Okay. Row reduce it. See how many pivot we have. 7. So let's just we have all the pivot. Do we have all the pivot? Everyone? Do we all get 3 pivot? Yeah. Yes. Okay. So we got 3 pivot. So meaning this system is consistent. Okay. Or there's a theorem. Remember the 4 theorem. If your matrix A have pivot on every row, if it is a square matrix, then its span R3 or span. Okay. Let me write down the statement. So every row in a n by n matrix has a pivot if and only if the column and are in. Yeah. So we have a 3 by 3 matrix here. So we have every row we have a pivot, then the column vector span R3, which means which means span Okay. Yeah. Every element in the polynomial we can write as a linear combination of P1, P2, and P3. Okay. So if you imagine, okay, try imagine if you replace Q as 0 vector. Okay. That means you change the right hand side to 0. Okay. So you still do the same row reduction. Okay. So what you care is really what? Is really both question you can reduce to one question, is to just reduce the matrix you get. Okay. And then check the pivot column. Okay. If every row have pivot, then it's span. If every column has pivot, then they are linearly independent. Okay. So satisfy both of them, you get a basis. Okay. Yeah. So really, 2 questions, only 1 question. So you just need to row reduce the matrix. Okay. Don't care what happens here. Don't need to care what happens here. Okay. Just reduce the matrix and then check whether every row have pivot column or not. Every column have pivot or not. Okay. Got it? Got it? Okay. Okay, good. Last one. Okay, last theorem for the day. So last theorem for the day is I mentioned this before, but I didn't tell you what the statement is. So the spanning set theorem. So what spanning set theorem is? So if you have p vectors in a set, okay, you have p vectors, and then you consider the span of them. Okay, so the span of them, by last time we already know that it's a subspace. Okay, so span of this vector is a subspace of V. Correct? Correct. So we have a vector space. Okay, so you can imagine something like this. Whenever have a vector space, you just draw a circle. Okay, we got a vector space, and then we pick some guy out. Okay, V1, V2 up to VP. Okay, we pick them up. Okay, and then we consider their span. Okay, okay. In your mind, what can you think? You can think of a line through them. Okay, line through them. Okay, because scalar multiple, and also we can take the linear combination of them. So you take a plane between them. Okay, all sorts of plane. If one of the vectors in X, say Vk, is a linear combination of the remaining vectors, then the set formed by X by removing Vk still span H. B, if H is not 0, then some subset of X is a basis of H. Okay, so what does this mean? So for example, let me see, I give you an example, try to make sense of this theorem here. So let's say we start with a vector space R2, okay? So we pick some vector inside here. Okay, let's pick some. Do you have a favorite guy or not? If not, then I pick. Okay, let's pick maybe 3 of them, okay? Okay, we pick 3 of them. And then we look at the span of these 3 guys. Okay, we look at the span of these 3 guys. Okay, and then the statement said if one of the vectors is a linear combination of the remaining vectors, the set X formed by X by removing VK still span H. Okay, so that means span of this, okay, is equal to if we were to remove one of them. Okay, in this case, anyone know what we can remove? Who can be written as a linear combination? So in this case here, you can see that 1, 1 is equal to 0, 1 plus 1, 0. Okay, so that means by this theorem, span of these 3 vectors is actually the span of 0, 1 plus 1, 0. Okay, actually they are the same. Actually they are the same. Okay, so you know why they are the same? Okay, because because everything in here, okay, everything in here is either A times 0, 1 plus B times 1, 0 plus C times 1, 1. Okay. But the claim is we can only just write this vector using two vectors here. Okay. Which is by substitute this equation here. Okay. So we can reduce this vectors into C times 0, 1 plus 1, 0. Okay, which is A plus C times 0, 1 plus B plus C, B plus C times 1, 0. Okay, okay. So you see this equation can go backward and forward. Okay, so they are equal. Okay, anything here can be written as three things here. Everything written as a linear combination of three things here can written as two things. Okay, so go down and go up. Make sense? Make sense? Sanqing blur, Sanqing. You okay? If you have any question, just stop me. Okay. So if h is not 0, some subset of x is a basis of h. So that means you can keep doing this, reduce your set until you get the basis. Okay, until you get the basis of it. If it is only 0, then it's not a basis. But if it's not 0, then it will be a basis. Okay. So in this case, right, actually this span of these two vector here actually is R2. Okay, using this example here. Okay, so this is the standard basis of R2. So there are two of them. So they span R2, and then check span and linearly independent, right? So you should check what you should check. You should check the matrix that formed by these two vectors. Okay, because you have okay, let me write something down. To see, okay, so from our discussion just now, so let me write from our previous discussion, we just need to check the pivot position in 0, 1 in the matrix formed by the column 0, 1 and 0. Okay, so if I swap the row also can. Okay, so easier. And then we can see that we have two pivot. We have pivot in every row. We have pivot in every column. Every row is span. Every column is linearly independent. Okay. Yeah. In this case, it's easier, but usually you need to do row reduction. Okay. Yeah. So the proof of this theorem follows from this example here. Okay, if you replace with general vector, you use a similar argument to show. Yeah. But that one is just math using max formality. But to understand it, you should keep this example in mind. Okay, you got a spanning set. If you have a linear combination, you can throw that guy away, and then reduce your set. Okay, that set still span, and then up to some point, you will find that they are linearly independent, so they form a basis. Okay, 5, 4, 3. So any question? Maybe ask some course related, lecture related, or quiz related question first, if you have just now. Just now, someone, you got a question just now? Yeah. Try. See? Try. Anyway, you guys need to practice English again, because you know what, I really seriously, because when I go to the working fair, right, okay, they say that Utah students is better because their public speaking is better. Yeah, so make sure your presentation is okay, how you communicate is okay. Yeah, so learn. Yeah. If not, someone has first can say first. Yeah. Yeah. Linearly dependent mean not linearly independent. Yes, correct. Hey, wait. Seriously. Okay, wait. Okay, actually, this one is a valid question, because in mathematics, right, sometimes not doesn't mean the other way. But in this case, yes. So let me write down. Yeah, so let me write. Yeah, sometimes in mathematics it's not directly. Let me see. So linearly dependent is equal to not, actually it's defined as not linearly independent. This is what you say, right? Yeah, because in mathematics we have something like the set is open and the set is closed, but not open doesn't mean closed. Yeah. So if in English, maybe they are opposite, but sometimes in mathematics it's not. Okay. But linearly dependent and linearly independent, yes, because if you go back and check your definition, they are actually negation of each other. Yeah. Not linearly independent is linearly dependent. Okay. Yeah. Sometimes I will say linearly dependent, sometimes I say not linearly independent. They all mean the same thing. Okay. They all mean the same thing. Any other question? Have you figured out what?
In the depth, find the base find the base for the non-space of A, and in it we row reduced. Yeah. And then we get the answer and write it as
Parametric vector form.
x equal to
Yeah, we call it a parametric vector form. Yeah.
And then you say the vector are independent, are linearly independent.
Yeah.
But your it's not
No, go on. Not general. My proof is general. I think my proof is general. Huh? Let me go back to the one you referred just now. What's the lecture again? You remember? 4. Okay. So the example is lecture 4. Okay, let's come back to lecture 4. This one? This one? This one? Which one? Oh, this one. Yeah, this one. Okay. So make it vertical. Okay, there's 2 more minutes, right? After 2 more minutes, if you want to leave, you can leave. I'll stay until all the questions settle. Okay, so for this question, right? Okay, so first actually he asked me about this y here. Okay, so do you need to write this? My question is no. My answer is no need. Okay, it's like what I summarized in the start of the lecture. After you row reduce your homogeneous system, right? You get the parametric vector form. Okay, and then these vectors here will form the basis of now A. Okay, this basis will form the vectors of now A. Okay, and then the second part of the question he asked, which is just now, he say that this proof here is not general. Not general. The second proof is not general.
You say it only has the, but it's to this.
Just for this example. Okay. I will say something. Okay. So why do I say this is general? Okay. Okay. Does everyone get this question? His question? He say that this method of showing that this tree is basis is not general. Okay, for the linearly independent part, right? Okay, it's not general. Meaning if I change my vector here, okay, then maybe I need to do it differently. Okay, so my argument is, okay, first of all, this one you don't need to write inside your exam, at least for tomorrow quiz. You just need to do up to here and then get this vector out and then say that these three vectors are basis. Okay, so to see that why it is a basis, okay, let's look at this linearly independent case property. So he claimed that this method is not general. Okay, so my claim is it is general.
Why you know it?
Okay, why I know it's general. Okay, so first of all, what's the nature of the vectors that you get from this now A? Okay, what you get is you will have a zero, a consecutive zero, and then keep reducing. Do you notice it? Yeah. Okay, so you can see that this zero is like every vector must have some zero or more zero, but and then the rest will be like increasing or decreasing up to depend on how you look at these vectors, but there must be zero at different places. Because why? Because this is the pivot column in your matrix. So let me show you. So the general form is something like this. So maybe like zero like this. Okay, let me try something. Something like this. And like this. Like this. So the general form is something like this. Okay, you can go on. But you can see that what you can see is toward the right of the pivot, right, must be zero. Okay, so if you want to have a span of this thing to get zero, right, for example, the last row here, there's no number you can multiply to, there's no non-zero solution that you can multiply to different vectors such that you combine to get zero here. You see, here only has zero, but here has one. But you want to make a zero here. The only thing you can do is put a zero here. So if you put a zero here, then similarly for the other, you also can apply the same argument. You can only put zero to this guy so that you only can get zero on this row. And then you can only get zero on this row, and then so on. So the solution is trivial. Because every entries to the right of the pivot is zero. This is due to the reduced row echelon form.
所以我想知道这个怎么来的。你为什么上个题能到这里啊？它中间
啊 What do you mean? 信号. No. The star here just mean you see. You see. The star here just mean only above pivot you can have 0, but other place you can have different thing.
那这个他们可以加出来的。
But let me think. Let me see. Oh, I think I get what you get. Let me see. Let me see.
从上面那个举到下。
Yeah. Okay. I get what you say. I get what you say. Wait. I get what you say. Yeah. How to go from that one to the other one? Let's see. I can't see it now, but I'll tell you later. But you can get from here. But my promise is you can get from here. You still get some this kind of pattern. You'll definitely get this kind of pattern. But I can't see now. Yeah, I can't see now. I'll tell you again. What I can't see now. Yeah, I will tell you later again. But the promise is you go from here to here. Okay. So this kind of pattern will appear here. Okay. Yeah. Okay. I will try and think carefully again. Then I tell you. Okay. But yeah. Okay. Any other question? Oh. Any other question? Try.
column
Column reduce.
没有横。
Oh. Oh, you mean like reduce like this? C. Use C instead of R. You use C.
Yeah.
I think column reduce will change the solution. Change the solution to the linear system. You change the linear system. The point that we use row operation is because we don't change the linear system. I think column reduction, column operation will change the linear system. Oh, to find column A. Find col A. Not sure. Never tried. Can try. Yeah, you can try. Yeah, because you can find row A, is it? So you want to use col A to find. Not sure. Can try. I never tried. Can try. Can try. And see. Yeah. Okay. Any other question? Please. Just chapter 2. Just chapter 2. So I think it's just so. Luo Qingrui asked me, right? Qingrui, who is Qingrui? Luo Qingrui. Is Qingrui here? No. Yeah, he asked me. Only 4 subsection we cover in the textbook. Yeah. Okay. And 4 subsection. Any more? Any more? No more? Okay. Have a good rest. See you tomorrow at 8.
哎呀妈呀！把我的脸给截掉，老师，把我的脸给截掉再放上去。
来，这个